Okay, what we're going to do now is we're going to derive the equation for current as a function of time. And the way we're going to do that is by using our old friend Kirchhoff's voltage law. So I'm going to start here and I'm going to go around there. This is for energizing, so we just flip the switch. There's no current at the beginning. We flip the switch and we're going to start charging it. Okay, so what we have is going around the circle E minus L di dt minus IR equals 0. So then what we're going to do is rearrange that, and so we're going to have E minus IR equals L di dt. Okay, so just put that over the other side. I want to get the i's together, so what I'm going to do is multiply both sides by dt and divide both sides by epsilon minus IR. So we have dt equals L di over epsilon minus IR. And that is an L there. L's a constant. When you integrate this, it's really, if you think of your substitution, your u is E minus IR. Your du would be negative di. So we're going to get a negative out front here when we integrate. So it's negative, and we get a 1 over r there. I'm sorry, a negative 1 over r. So we get negative L over r log of epsilon minus IR. And on this side, we get a t. I'm going to put a constant over there when we integrate both sides. Okay, then I'm going to multiply both sides by negative r over L. So we get r over LT plus C equals log of epsilon minus IR. Clearly, we're going to want to do e to the each of these. So we end up with e to the negative r over LT plus C equals epsilon minus IR. And I'm going to save a whole lot of time. Really what happens, e to the negative r over LT plus C is the same as e to the negative r over LT times e to the c. E to the c is just a constant. K, I'm going to call it K because I don't like C. That's capacitance. Equals E epsilon minus IR. Okay, so after a lot of rearranging, we get I is epsilon over R minus K e to the negative R over LT. If we set T 0, we know the current will be 0 at time 0. So this is epsilon over R minus K, because e to the negative 0 is 1. K is equal to epsilon over R. So I is finally, as a function of time, epsilon over R 1 minus e to the negative R over LT, having factored out the epsilon over R. And so remember the RC time constant? Now we've got a L over R time constant. And that L over R time constant can help us figure out when it's 63% of the way to the final value, either the current being 63% of the way up to the value, or in the case of the voltage across here, 63% of the way down. Because right when we hit that switch, there's no current through any of this, no current through R. That means all the delta V here has to be across the inductor. So as soon as you throw the switch, that voltage across this goes up, this stays 0, and then slowly as the current gains, then the voltage across the resistor gets bigger, and this eventually acts like a wire. Okay, now let's look at this one. We're going to actually just see how these curves go and get general equations that we can use. Now, when I throw a switch from the middle, charging to A, as I said before, what's going to happen? At the very beginning, the current was 0 before, and it's got to be continuous. So that very first data point is going to be 0. and it's going to go up from there. As time goes on, more and more current goes through there until this behaves just like a wire. And so all the delta V is across the resistor. So it's going to have that nature. Okay? And at the very end, the current is going to be this epsilon divided by R. So it's going to asymptotically approach epsilon over R. And now if we look at the voltage across the inductor, well, it's actually easier. Let's start with this. The current is 0 at the beginning. We just established that. 0 times R means there's no delta V across that. That means this delta V has to be epsilon. So at the very beginning, and it's very non-continuous because before we threw the switch, there was no voltage across that. There was no current going through it. It was just acting like a wire. All of a sudden, when we close it, it jumps up like that. Okay, so in a capacitor, remember, the current was discontinuous. The current could switch instantly, but the voltage couldn't because the charge couldn't change in a capacitor. But here, the inductor, the current can't change instantaneously, so the voltage does, and that's going to go down. Whereas in the resistor, the current goes bigger and bigger, and it will asymptotically approach epsilon. Okay, so being able to do that, now we can actually write our equations. So we've seen I already. Let me just do this one because this is slightly different. VL is going to be epsilon times, instead of 1 minus, it's this declining exponential, e to the negative R over LT. Right? VR, if I had to write that, VR is epsilon times 1 minus e to the negative R over LT. Okay, so we can come up with the general forms very quickly. Now let's look here at the RL circuits. And okay, we've got a lot of current at the beginning. Remember, at the very end, it's acting like a wire. The inductor's acting like a wire. So at the very beginning, that current can't change quickly, right? But it can start to decline. And I shouldn't be doing these T1s. Oh, I'm sorry. I had this as throw the switch to B at T equals T1. So in other words, this has charged up, and then I throw the switch, and it's going to do this. It's going to be an e to the negative RT over L function. And the initial current was epsilon over R, right? If this is a wire, the current is going to be epsilon divided by the resistance. Now VL, and let's copy it from above, that when you charged it, VL eventually went down. That's a terrible drawing, but it asymptotically approaches 0. When you throw that switch over there, let's talk about what happens. This current continues. So whatever the current was just before has to be the current just after. It's still a high current. That means this delta V is going to be epsilon 0. And what we found before was this for a charging circuit. It charged, it got up to that. Then we throw the switch, and that starts there, and it will slowly, as the current decreases, the voltage across the resistor will decrease. What happens to the voltage across the inductor? Well, look at this. This circuit right here is now what we're talking about. So basically, whatever the delta V is across here, this has to be the negative of that. I really am not going to worry about signs. I'm going to put magnitude of VL. Because when we flip that switch, all of a sudden, that's actually going to be a negative. Because if we think of that current, I've got the current going in the wrong direction, of course. Current in this direction. If we look at this is positive, this is negative. So this end of the inductor would be positive, this end of the inductor would be negative for Kirchhoff's voltage law to work out. So this would actually be a big negative number and declining, but if we just talk about the absolute value, it'll go like that. And again, in the long term, this acts like a wire. Now, the equation for stored energy in an inductor, and there is energy stored. I mean, we saw in that previous situation, we had a we had a current going in through the inductor and the resistor, and we had some current going through that. It was charged, and then we flipped the switch over here. And you can see that when we throw that switch back, there is current going through there, and there is still current going through there. It acts kind of like a current source. So this is the energy that's stored in there, and it takes some time to transfer that energy so it gets dissipated by the resistor. So when we throw the switch back, the stored energy in the inductor ends up getting dissipated by the resistor. And if we have an EMF of 12 volts, a resistance of 40 ohms, and L is 0.005 Henry, how much energy is stored in the inductor's magnetic field when the current reaches its max value? And I'll give you a moment to think about that. Okay, so the max current, I max, was, again from the previous circuit, epsilon over R. So it's going to be 12 over 40, which is 0.3 repeating amps. So there's our maximum current. How much energy is stored in there? UL 1/2 times L, 0.005 times 0.3 repeating squared. And that equals 0.000225 joules. 2.25 times 10 to the negative 4 joules. That's how much energy is stored in that inductor, and that is how much energy will eventually be dissipated by the resistor. Okay, these are a couple of questions that are very easy, and one question that's a little more complicated. Find the current in the 10 ohm resistor when the switch is open. When the switch is open, no current is going through that leg at all, so it just ends up being 30 volts divided by 10 plus 20, 30 ohms in series, and that's just 1 amp. That's pretty easy. Okay. Find the current in the 15 ohm resistor when the switch is first closed. Well, when the switch is first closed, the current is 0. It was 0 before it was closed. It's going to be continuous. 0 after. That means this must have 0 amps going through it. Now, harder is find the current in the 10 ohm resistor when the switch has been closed for a long time. Okay, so you close that switch, current will slowly start going through there. Okay, because at the very beginning, there is 1 amp times 20 ohms. There's 20 volts across there. When you close that switch, right, that 20 volts will eventually start building up current through the 2 Henry. Okay, notice, by the way, in this, we don't even end up using the value of the 2 Henry inductor. So in the long term, this becomes a wire. After the charge, it has adjusted to the charge that's trying to be pushed through there. It becomes a wire, essentially. So then we have this in parallel with 15 ohms. And when you do 20 ohms in parallel with 15 ohms, the resistance ends up being 8.57 ohms. And then we do that in series with that, 18.57. So ultimately, the current ends up being delta V 30 divided by the total resistance, 10 plus 8.57. And you end up with about 1.616 amperes. An LC circuit is a really interesting thing. So we charge a capacitor to some Q max, and then we close the switch. When we close the switch, we have positive charge over here, negative charge here. Positive charge will start flowing gradually at first because there's no current there. After a while, this becomes, as more current goes through there, current goes higher and higher. Eventually, when there's no charge here, this has a current moving in this direction. So it's going to keep a moving charge through until the polarity is switched. And then the whole process starts over again. So this is called an LC oscillator. Okay, oscillator. So let me show you how that plays out in the realm of differential equations. Okay, if we have, let's go around that circuit. Q over C is going to be the delta V here. And then plus L times di dt has to be equal 0 going around in a circle. Okay, so if we take this I and put it on terms of Q, this ends up being L, the second derivative of Q with respect to time. Q over C. Okay. And then I'm going to get the QC on the other side, Q over C, and I'm going to divide both sides by L, and I'm going to write that L first. Okay, so negative Q over LC is d squared Q dt squared. All I did is rearrange that to get that second derivative alone. I'm hoping you might recognize now you've got a second derivative that is some negative constant times the variable itself, and that's simple harmonic motion. Okay. And if we look at this, for example, if we just say Q equals cosine of some angular frequency times time, and I'm saying cosine because that Q started at some positive amount. So it's a cosine. We could do a phase angle, but we're not going to worry about that. Q dot or Q dt ends up being negative sine, negative omega times sine of omega t. And then Q double dot equals negative omega squared cosine of omega t. So we can see that Q double dot is equal to negative omega squared times, right back where we started, Q. Okay, so if we compare that, and I've changed notation, but this is Q double dot, there's Q. That means that the omega squared is 1 over LC, so omega is 1 over square root of LC. So what we've kind of demonstrated is that this is going to oscillate back and forth. That charge is going to go like this, oscillating back and forth. Current will do likewise. That'll just be the derivative of this, with a frequency of 1 over the square root of LC.